Ooh. All right, so right, that was loud. All right, guys, so we are live here at Go Miami, and I'm Bill Kennedy, Go Miami, and tonight we have a really special guest all the way from New York, from MediaMath, Prasanna, and he's going to talk to us about scaling data ingestion systems, which is a lot of what he's doing over there in MediaMath. So take it away, man. Appreciate your time.
Thanks, Bob. Absolutely. Can you guys see my screen?
Yeah.
Okay, great. Yeah, so MediaMath is an ad tech company that helps media planners, buyers, and agencies buy advertising across the internet. We have a marketing technology platform called Terminal One. So how many of you guys are familiar with online advertising, or what we would call programmatic media buying?
I know I've done some of it, but not probably to the scale you're talking about. A couple people raised their hands.
Okay, cool. So let's imagine a web page for simplicity, maybe like a basic news site. You see ads on the page, like a banner across the top, a few on the side. A lot of these ads actually start out as containers. So when the page loads, the site holds an auction through an auction house or an exchange and gives a space to the winner. So around the web altogether, there are over 120 billion auctions daily. And each auction, because it needs to start and end before the page loads, needs to happen in milliseconds. So in order to even participate in these auctions, you need to have a global platform that can scale intelligently to keep up with this media supply. And this is where MediaMath comes in. So our clients come to us with their creatives, the images, videos, whatever their ads are, and their desired outcomes, including things like what kind of user they want to target, time of day, and their desired outcome of driving users, for instance, to purchase a product. So we then go and bid on our client's behalf on these ad spaces. And so our servers currently handle around 2.3 million requests per second. And most of those, because they are bids, and because it has to happen in this band of milliseconds, happen in under 40 milliseconds. We have about 120 terabytes of data that we analyze on a day-to-day basis to help optimize these campaigns, 9 points of presence, and a bunch of stuff in the cloud, distributed through about thousands of servers. And as a company, we use a lot of languages and technologies to solve these problems. So I led integration engineering at MediaMath for about 3 years. I currently do developer relations, as I had on my first slide, but this talk is going to be about our data. It's going to be about a history of how we have done data integrations and how we used Go to solve problems that we had when we tried to scale and extend these data integrations. So just want to start out with some results just to get a sense of where we're going. By the time that we switched to Go, all of these things happened. Our batch process times decreased dramatically, capacity increased by orders of magnitude. Streaming activation, so like HTTP, short-term data went down to near real time. Deployment time and the pain of getting things live, getting new features live, went down a lot, and parity issues between QA boxes and production boxes basically went away altogether. All right, so how did we get here? Where did we come from? The particular segment of ad tech that's relevant to this talk is finding an audience. So both in online advertising and offline, more traditional advertising, finding an audience is a very important component. And advertisers use different strategies here. They want to find users who they know are interested, and they want to discover and classify new users who may or may not be interested. But they want to find users who will be. And a number of companies tackle this problem in different ways. So for instance, one company may claim to accurately determine which users are male and female, and which users make over $100,000, less than $100,000. While another company may claim to match offline users to online cookies. Additionally, advertisers and brands often have their own CRM systems and their own sort of databases of users that they'd like to bring in. So if you have, if you're a loyalty member at Gap, for instance, they might want to target online ads to you. So to meet this functionality, we should be able to ingest this data. We should be able to allow clients to upload their own audiences, upload their own CRM systems. We should allow data providers, these companies that are classifying these users and want to offer these audiences to the brands and advertisers, to upload them into our system. So we need to take in lists of users and segment membership. We need to allow different input formats and interfaces into that, and I'll get a bit more into what that means in a second. And we need to build something that scales, because when we initially built this around 2010, we didn't really know how much data we'd be getting. We wanted to build something quickly so that we could meet the demand, but we knew that it was going to increase in some form or fashion. So when I say different formats, we want to have some way of interacting with the system over HTTP, and we want some way to interact with the system more in a batch in a batch format. So because there are many different needs for these users, they might want to upload a giant batch at once. They might want to do remodeling in different shorter term formats. So we need to have a way to meet all of this, but have a sort of common specification. So the sort of initial architecture we came up with was to have these two interfaces, FTP and HTTP. And the primary interface would be FTP, because for most offline data, or more, most data that's determined in an offline fashion, batch processing is a very, very good use case to meet. So oftentimes the update cycle that these companies and these providers will have is much longer. So on the time scale of hours or days, so we can ingest these files every few hours and essentially be fine there.
Hey, let me interrupt you for 1 second.
Sure.
Have you been going through your slide deck? Because for some reason we still only see the first slide.
Aha. Yes, I have been going through my deck.
So we're seeing what's the program called again? PowerPoint. Yeah.
You're seeing the actual, okay. Let's see if I can figure it out.
Yeah, that's better.
Okay. Okay. Awesome. So let me just back up a second and let's go slides real quickly. Attack. So yeah, it's about our data. Here, the results we found. Want to find these audiences and create a system that allows both the clients themselves and data partners to upload audiences. And we have different kinds of formats that we want to meet, different kinds of specifications that clients and partners will have. So here is what I was going through earlier. The real-time data coming from HTTP is more real-time, where a time scale of hours isn't really good enough. It's a bit too slow for that. So we need this different processing the profiles, but essentially a common backend. So the processing itself is handled by a series of translation steps to convert these different inputs into a common format that we defined internally. And then we had an application to load these all into a database, and then that information would get pushed to our globally distributed bidders, and if thus we can bid on users. So how we set this up, early in MediaMath's history, we loved Perl. The architects behind many of our systems, including our campaign management API and this initial data ingestion system, loved the language's tools, community, and style. So as the core component of this is translating streams of text, we chose Perl for these capabilities and for the expertise of our architects. So again, here's kind of how it went. The Perl step was more of the middle step, the convert to DB loader format, which, oops, is there, which we foresaw to be the more the more intensive case of this. So from the architecture, we designed essentially a Perl input stream that would take these different sources, convert them to a common one. Each one has some slightly different configuration, but they all sort of go into one input process. So success. This worked fairly well. We could handle gigabytes of data. Volume was consistently going up, but we could process batch files a few times a day, process HTTP data a few times an hour, and all was good. The talk is done. But unfortunately, or fortunately really, this process of ingesting offline data caught on throughout the ad tech world, and all of a sudden we were swarmed with providers and clients that wanted to purchase real-time bidding media on their own data. So we had two main problems here. We had to figure out how to handle this massive influx of volume where throwing servers at it becomes pretty expensive. And we had to figure out how to deal with other input formats. There were some providers that couldn't adhere to a single specification, or had, or just had a very different one that they couldn't go away from. And so we had to figure out how to handle all of these different things and still have something that scales. And so when it came to looking at the code base and how it sits, we kind of had two main options here. We go from our runtime flexibility, right? We add this dynamic system into the runtime, which feels more dynamic, and it's a bit simpler for ops because they only have to deploy, essentially one thing. There's one front end for everything, and again for developing as well, it's the same thing everywhere. Or we could go for a method that had independent processors, so something that essentially had a different executable, let's say, for every different format that we had, and this would make it focused and optimized, and we can make sure that it was fast, but it was also duplicative, right? Necessarily, we were duplicating work in having these independent executables that were doing very similar things. But we ended up going with that more. So we first went with the runtime flexibility, but then we ended up having to go with the independent processors, and so our the way that we handle our input kind of from the start went out to separate places. And this started to scale a bit better. It was still tough to work with though. And we didn't really have any built-in tools for concurrency there. So we designed a system that had, that used Linux processing controls to parallelize it. And so the way that this worked kind of ended up looking like this. And so this is actually how our production code was run for some time. Pipe the files out of the input into GNU parallel, into the translator, into a parallel implementation of gzip, all of which were stored as just massive config files and shell scripts that iterated over it. And I mean, if this doesn't already look terrifying to you, the nearest DevOps expert you can talk to will cry at the sight of this. And so this actually, started to stumble us. Our data volume kept on going up. Once again, pushing the limits of our architecture. Without wanting to throw more hardware at the problem, but Splitting our processing over many machines brought deployment problems, right? When we have a configuration that is that confusing and that complex, you're going to have problems with configuration. You're going to have problems with deployment. And so we needed to rethink how we handle all this. And so we started to think, what if we did something else? And we have a strong culture of experimentation. If you've got an itch to solve and we have a problem and you come up with a good solution to solve it, then we try to minimize barriers to seeing the results. This was a system that was staggering over. I mean, it was absolutely, falling over itself. We had spent some time as a company experimenting with Go before. I had spent some time learning Go. This was about a year and a half ago when we did this, so around the end of 2013. And I was curious if we could use Go to solve this problem. Really, because the two main things we had problems with, I thought Go was very well suited to solve. Right, concurrency and parallelism, we were having a lot of trouble handling it with this huge, massive, complex pipeline. And so if we used Go routines and channels, could we make that a lot simpler? And having an extensible architecture without a massive deployment and DevOps overhead. So what about interfaces? Could we have something? Could we have some system there where interfaces help us out? And so we begin by tackling the concurrency problem. So that actually proved to be probably the easiest part of this whole exercise because of Go's fantastic primitives, channels, and Go routines. So this is an example of a fan out and fan in pattern described on Golang blog. So we use these to take data from our files, send them through different processors, and bring them back all together. So the fan out, I mean, I'm sure some of you have seen this before, but always helpful to see. This fan out pattern, all it does is takes all the lines from a file, iterate over using a buffered IO scanner, and pumps them into a channel. Returns a channel for the processors to use. And you'll notice here that we specify a second argument, buffer. When you make a channel in Go, you can also include a second argument to specify how many items can be pending in the channel. So if you specify a buffer of 1, then if the channel sends one string, or if the Go routine sends one string into the channel, it will immediately continue, but the second string will not be sent until the first string gets received. If you have a buffer of 0, the first string itself will be blocked until the receiver is ready to receive it. So we can then distribute this data from this channel to multiple workers by creating a pool. So the workers argument here, which is the capacity of our slice of channels, is a command line flag that indicates the number of workers had. And so then for each workers, we go and send this channel into it and allow it to populate. And so it should be clear that something like some pattern like this is a boon for ops teams. By being able to tune the processing behavior in an application itself, we remove the need for dependencies. In this case, GNU parallel and the intricacies of having the dependency management. But even nicer, it allows everyone, the devs and ops and everyone, to more easily benchmark and test more accurately. So on the local machines, we as developers test different settings, test to see how different workers affect execution profilers, and we can benchmark and compare these according, over time. Then we complete the fan in by bringing all the data from those different workers into one. merge channels here is a function that spins a Go routine for each worker in the pool, and it sends its output to a single channel. That channel gets returned, and so we then just pipe that back out to an output. And then we return the output, and can't handle that either by sending it to a file or by sending it to the next stage of the pipeline. So the entire function then looks something like this. This is almost this is almost entirely what it is. So all of that comes together pretty simply. There's really not that much code here, but there is a lot of really interesting concurrency going on in these few lines of code. And taking advantage of command line flags, the architecture slide that I showed previously, go back to it, it can look something like this. All right, so what did we learn from that? Having lots of concurrency controls is both a good and a bad thing. Go max procs, for instance, you'll notice that this command line flag of workers says how many Go routines to spin up, how many workers to add to this pool. I didn't say anything about Go max procs. The Go max procs is the number of logical processors your code can run on, whereby the runtime will bind Go routines to logical processors that get bound to OS threads. Effectively, the number of OS threads your code can run on. And increasing Go max procs doesn't automatically make things faster. If you have a lot of concurrent code, it may not automatically scale across multiple processors, right? If you have lock contention, blocking, race conditions, there's a lot of stuff that can affect how it works. So as a quick note, the default Go max procs equals 1 doesn't stop OS calls from running across multiple cores. It just stops the runtime from scheduling things across multiple cores, or across multiple threads, rather. And so Go offers some really great tools to help deal with this. Testing.b for benchmarking and pprof. And if you haven't seen pprof before, because I hadn't seen pprof for a while when I was first doing this, it is absolutely fantastic. It is a built-in profiler, and we use it all the time to profile our code. It's a sampling profiler, and it comes with both visualization and command line tools. So it tells you how much time is being spent in each part of your code. It tells you what you're allocating, and it's really just very useful for understanding what your code is doing. This actually is not the profile output for this particular process. It's for the HTTP server that we have. Defer is slow, something that we learned, right? Defer is absolutely fantastic. It makes things so easy, right? And when we have things like, a lot of conditional processing happening, right? You want to defer things like unlocking mutexes, right? Closing files, things like that. Defer is, in this case, which was a benchmark I did on my laptop, but asked a couple of other people to do as well, and it's pretty close. Not deferring the mutex unlock is 3 times as fast, or it performs 3 times as many operations per second as using defer. So while it is a fantastic tool, it is another thing for Go to keep track of in its scheduler when it's unwinding the stack. So be judicious about where you use it, and use it when trying to get around it would make the code a lot less readable or workable, etc. Okay, so we talked about the concurrency and parallelism problem. Now let's talk about interfaces and how they helped us. So interfaces, fairly common pattern in Go to create an interface to have a collection of common methods. In this case, if you notice, I didn't actually specify what a tokenizer was above when I showed the entire processing function. The tokenizer is just an interface, and all it does is it processes or it parses each different input format into a token stream. We then have a common processing function that acts on this token stream and produces an output. I omitted it here for brevity, but tokenizer interface works with this internal function to send this token stream into an output, and the process lines method sends that channel back in. And so when we merge all those things together, we end up getting the output that we want. So after implementing interfaces and going back to, after going to channels, we ended up with right back where we came from. Right, the architecture looks basically the same from a code standpoint. We have this input, we delegate it by choosing the right interface, have a different config for each one, except that A, it's a lot simpler just in the way that we're handling each of these, and B, we were a lot faster. And how much faster were we? With a naive rewrite, it was an order of magnitude faster, and we eventually got it, had even more performance eventually after that. Okay, so I went into detail about the batch processing. I'm not going to go into as much detail about HTTP streaming, mostly because we had a lot of the same goals and tactics there. And what GoSpeed really helped us out with in the HTTP case was the feature set that we were able to add to this. So here is how we started off with HTTP streaming, right? We had a time scale of minutes in between the time that an HTTP request was made and we were able to bid on the user. So anywhere from 5 minutes to 15 to 30 minutes, which I think 15 was about the average. We had a very primitive system of authentication authorization. We had to essentially restrict what our partners and advertisers could send to us to make sure that it wasn't conflicting with anything. And that was simply because doing those extra checks would take too much time. And the richness of data that people could send was limited. And so when I say richness here, I mean things like custom timestamps and both additions and removals and some complex logic with combinations of segments. We couldn't really handle that and still have this latency requirement of minutes. So with following a fairly similar method to the batch processing, but using net HTTP here, the HTTP.server is actually public facing, and that is just, again, in the spirit of helping our ops team deploy this. That is a huge boon to us. But so we're able to simplify our dependency management there, and the default server behavior spins off a new Go routine for each request that comes in. So we got concurrency built in, and it fits the model that we had. One thing that we discovered as we were trying to speed it up and make it more efficient was sync.pool, which was introduced in, I believe, 1.4. It might have been 1.3. Sorry, I don't remember that. But the sync.pool that came into the standard library is made for short-lived deterministic resources. So what do I mean by deterministic? I mean that if you're not entirely sure when the resource is done, when it's ready to be put back into the pool, then this doesn't really help you. But if you can deterministically say, I know when this will be done, I know when this goes back into the pool, and I know, and I have an idempotent method to reset it back to an effective zero value of your type, then a sync pool can help out a lot. And in this case, it helped us out a lot. It essentially halved the execution time of any given request, and made our memory profile much more simple. And again, profile, right? We used pprof to see the effect that each of these things were having, and there are people that aren't quite sold on sync.cool, and we felt the same way. We weren't sure if it would work for us, but through profiling and benchmarking and using the tools that Go has built in, we were able to see just how much it added in. So there's one more feature that we were able to tackle here, the actual latency of how long we were able to get these in. We were able to handle so many more requests at such a high throughput that we were able to add another component into the system, a component that would send requests directly to our bidding infrastructure in real time. So by allowing a consumer of this, so a data provider or a client, to specify a region where the user is in, effectively a continent, we can bypass any of the minute scale batch processing methods that we had and just go directly to our bidders. So while previously we couldn't do this because of latency and scale issues, we were able to do this, and our bidders can now target this data, target users within a time frame of a few seconds of exposure. And the simplicity and speed allowed us to actually adapt that component to a microservice-oriented architecture. We have been moving over the course of the past year or so to something that's a bit more microservice-based, feeling the pain of having single large code bases, trying to split them out to make them more independent. And this was something that then allowed us not only to adhere to that sort of philosophy, but allow other producers to use that service as well. So not just from a philosophical component, but from a practical component, it allowed us to expand that way. And also allowed us to support those richer forms of data and authentication and authorization. So in the previous system, we effectively had a wall between data sent by data providers and data sent by clients. We let this data through that needed to go through by an internal mapping process that was a bit complex, it was a bit painful. So instead, we were able to simplify the process, add a bit more complexity into the HTTP server, but still handle a whole ton of traffic and allow clients and providers to share data natively when it worked for them. But what our ops team loved most about Go was that it compiles to a statically linked binary. So we don't have any runtime. We don't have any runtimes to ship alongside our executable. We don't have to worry about that, and it cross compiles. So, from my machine, I can compile for all of our production servers, send it to, for instance, an S3 bucket, and have them pull that down as part of the deploy process. And the dependency of having our code in an interpreted, dynamically run language introduced a necessary runtime dependency, into our deploy process. And this can be straightforward to manage, but it doesn't lend itself to things like old versions of a specific runtime, more specifically, old versions of a runtime that aren't actually shipped with the OS that you're using in production anymore. So we actually needed to take complicated measures to ensure that prod servers are running the right versions of these runtimes. And it actually has led to issues with parity in production. So, our DevOps team was all on board. So we had our DevOps team on board, our devs were on board, but, we still had to convince management, right? And I mentioned that we have a pretty strong culture of experimentation, but, we still need to convince somebody to allow us to deploy this to our production servers. So Go's tooling here is really what saved it.
Let me interrupt just 1 second. We're about 40 minutes in now, so we gotta kind of, we can kind of close it up. Is that okay? I'm sorry.
Yeah, well, close that now or just speed it up?
Kind of speed up. Normally the talks are about a half an hour tops, so we're about 40 minutes in. Just have to kind of wrap it up. I apologize.
Got it. Okay, that's no problem. My apologies. I think I'm a bit long. So essentially, we use Go test. Go Fumped is amazing. So we were able to convince people to let us ship it. Summary I talked about earlier, but last thing is that lines of code actually went down by reducing all of by splitting apart our processes to handle scale. We ended up having a lot of duplicative code, and through the very simple primitives that we had with Go, we actually reduced lines of code. All right, so that is our story of how this one particular pain point ended up being a lot easier with Go. Some of the things that we did to help solve it. Thanks a lot for listening, for being here.
I have one question for you. How many people were coding on this project?
This project started off with just one. It was just me to have the initial proof of concept, and ended up being about 5 people for both of these systems.
And those 5 people were part of the Perl team, or you brought in 5 new people that could just do Go?
It was a combination of both. 2 of our members had also been on the Perl team, so we had essentially been moving people around. They had started building some other systems in Go as well, and 2 of the members had been working on other Go projects before.
And what was your biggest challenge is taking, because how much Go experience do these people have when you brought them in on the project? Like, what were some of your challenges there?
Yeah, that's a great point. I would say that there is this concept of idiomatic Go, right? That is sort of like your code should be clean and readable, but also formatted well and not have too much in the way of allocations, and also be very efficient, right? And so it's this sort of there's an idealistic view of how your Go code should be that that did cause a good amount of pressure. It caused some. I will put it this way: it caused some fun code review and pull request strings and conversations there. But I think that what really helped us in that case was just the simplicity of the language. Right? Go is such a simple language that at the very least for most of these people, the learning curve to get up and running and start writing code was pretty low. Most of the members of the team, anyone or everyone who had come to Go from other places, were able to pick it up and start contributing meaningfully, in about a week, I'd say, and getting to that that holy grail of idiomatic Go is something that maybe we still have some discussions around, but meaningful contributions were pretty quick.
Right. Yeah, because you actually showed some fairly complex code there with channels being write-only channels, and I mean, some of that, you wouldn't have anybody just on the team start writing that. So what kind of advice would you give to someone who's thrown into your position? Here, we're going to port this thing to Go. You're going to be the lead on here. You're going to have 5 developers. I mean, from a management standpoint, how did you learn how to work with each of those team members? And was it a lot of code reviews? Was it people working together? You understand what I'm saying?
Yeah, absolutely. Yeah, it was a lot of code reviews. We have a few other people within the company that had been doing Go for longer. So it was a lot of asking them for good pieces of code to look at. The standard library, for instance, is sort of one of the go-to responses for where is some good idiomatic complex Go code that I can go and read and sort of try and understand what's going on there. So it's a lot of code review, a lot of asking other people. We use hip chat within the company to have communication, kind of like Slack. And so we had a Go room there that gets a lot of traffic.
All right, excellent. I don't know if anybody else has a question for him. No. All right, man. I really appreciate your time. Sorry I had to cut you off a little bit. But it was really a great talk. We've got it on video now, which is awesome. And we'll get all that posted. So again, I really, really appreciate your time.
All right, great. Well, I had a great time.
All right, thanks.
All right, have a great day, guys.